Hello everyone, I'm Norman Wildberger, and today we're carrying on with our understanding of geometry for sociologists. Sociologists wanting to delve into this mysterious clique of pure mathematicians to find out what are these people really doing? How can we separate the gloss from the essential sociological struggles that perhaps are going underneath the surface? Now, the European time is very interesting because starting around the 16th, 17th centuries, Europe starts adopting and understanding the earlier Greek and to a certain extent Islamic works and starts moving beyond them, starts developing new forms of mathematics and in particular new forms of geometry. So the story has in fact all kinds of different geometries, starting with Cartesian geometry, projective geometry, which we've already touched upon a little bit. Some new development called descriptive geometry that plays a big role in industry and applications. Algebraic geometry, non-Euclidean geometry, which emerges eventually in the 19th century, as does Riemannian geometry and differential geometry. And there's also complex geometry, affine geometry, and probably more. Okay? So even until the beginning of the 20th century, we had this proliferation of so many geometries. And this was quite against the spirit of the philosopher Immanuel Kant, who asserted that human beings have an innate intuition about geometry. It's almost built into us. The three-dimensional space in which we live in, that's kind of God-given, and that's pretty well all there is. So this pure mathematical point of view here, which has all these multifaceted aspects of things, really starts to weaken the Kantian position. And in some sense, I think it's really an important precursor to the development of pure mathematics as a mature discipline, as people started to realize that there is more than one geometry. Now, I'm going to give you a necessarily simplified view of things here. If you want more information, please have a look at my History of Maths lectures, where some of these topics are gone into a lot more detail. So a really pivotal event which separates the geometry of the ancient world and the modern geometry is the development of Cartesian geometry, largely by René Descartes. But Fermat also made important contributions. Descartes was a French genius with a lot of abilities in different directions, and he realized that you could rethink the Greek geometry in a more algebraic way. And so the idea is that by introducing suitable coordinates, geometry can be reduced to algebra and ultimately to arithmetic. Now, the way Descartes did this is not exactly what modern people regard as Cartesian geometry. That actually came a little bit later, but the essential idea is in Descartes. And by the way, Cartesian refers to the carte here. So Descartes in French means from carte, carte being a place. So that's where the name comes from. So the basic idea is that, let's say we're talking about planar geometry. Here's the plane. Instead of just having a white board on which we start drawing lines and circles and such, which was sort of the Greek point of view, Descartes says, let's start with some coordinates. Okay, and the simplest way of introducing coordinates, perhaps, is to introduce two axes, these days called the x-axis and the y-axis. And we mark off equally spaced coordinates on these axes, 1, 2, 3, 1, 2, 3, etc. In Descartes' day, interestingly, he did not believe in negative numbers. So this usual story that's presented is actually not in the spirit of Descartes. Descartes liked positive numbers, and negative numbers were some weird kind of thing that was somewhat dubious. But anyway, these days we think of these numbers as representing positions, and so we can describe positive numbers in this direction, negative numbers in this direction, so we're covering the line. Okay, so when we have that, then we can specify a point say this point A, by a pair of numbers, 2, 1, meaning you go 2 in the x direction, you go 1 in the y direction, and then you use sort of parallel lines to pinpoint this point A. Okay, so points then become ordered pairs of numbers. Okay, and this is the critical thing, that then the geometry becomes essentially built up from a prior theory of arithmetic. Okay, this is such an important development that then allowed all further manner of things. Descartes realized then that lines, say like this line here, could be described by a linear equation. In this case, the equation x minus y minus 1 equals 0. Okay. What does that mean? It means that any point that lies on this line, like this point A, has the property that if you take the x coordinate and you subtract the y coordinate, and then you subtract 1 more, then you always get 0. So this equation becomes a characterization of this line. So a line is no longer something that you draw, that you have to describe in some rather vague way. It's a line which is straight or something like that. No, to Descartes, the essential aspect is that it's given by an equation which is linear in x and y. Linear means there's no squares, there's no cubes, there's no square roots. There's just x and y and multiples of x and y and constants. So once you've adopted this point of view, then Descartes realized, well, you could go further pretty quickly. So the conics, which had been studied extensively by the ancient Greeks, he realized you could capture them by considering quadratic equations. Okay, equations where you're allowing degree 2 expressions in x and y. And then it's not such a big step to go to cubics. And Isaac Newton spent a lot of time thinking about cubics and trying to classify cubics. They correspond to cubic equations. So you see this entire pantheon of curves, which are going far beyond what the Greeks were able to do, can be sort of immediately invoked, because now you're just considering equations which can be rather arbitrary. The analysts of the day, calculus was also being developed in the 17th century, adopted this framework as a way of positioning and describing the functions that they were interested in. So in the 18th century, Euler and others started advocating the idea of a function that, say, y is a function of x, say 1 plus 3x plus x cubed plus x to the fourth. So that's relation, it's a functional relation. And that could be described by now a curve, because if you just ignore this, you just look at this, this is an equation in x and y of degree 4, and this is something of its graph. So this gives analysts, people doing calculus, a direct geometrical framework in which they can talk about slopes, areas, tangents, the kinds of things that they like to do in calculus. But it's not just the plane, it's also extending into 3 dimensions. So a consequence of this is that when we go to 3 dimensions, we can now start thinking about the space that we're living in, also in terms of coordinates. And it's really the same idea. So now we just need 3 axes, say an x-axis, a y-axis, and a third axis in the perpendicular direction, say the z-axis. And then we could have equally spaced markings on each of the axes, and that would then allow us to describe the position of any point in space by a triple of numbers. Okay, and that triple of numbers then is an arithmetical encoding of space. For example, this point here, okay, if this is the x-axis, we have to go 1 in this x-axis direction. We have to go 1 in this y-axis direction. That would sort of get us to this point here. And then we would have to go up 2 in the z-axis. So this point would have coordinates 1, 1, 2. And then you could talk about analogs of these things in this three-dimensional space. And in some way, it's quite analogous to what's happening in the plane. So a very powerful framework then for understanding the world in which we live in. Interestingly, around the same time, another Frenchman, Desargues, was developing a completely different kind of geometry, which was more novel and did not have a long connection with prior work from ancient times. There was an earlier theorem which ultimately was realized to be projective geometry. That was Pappus's theorem, but that was really sort of an exceptional thing, and Desargues more or less created this new kind of geometry from first principles. And it was a geometry which was in some sense simpler than Euclidean geometry because it was only concerned with points and lines and incidents between them. So the notion of when a point lies on a line is a notion that you have, but you don't have perpendicularity and you don't even have the notion of parallel. So it's a kind of a simple-minded kind of geometry. But it turned out to be really crucial in laying a foundation for all of geometry in the 19th century. But it took people quite a long time to figure out just how important projective geometry really was. Desargues contributed not just this new framework, but he also contributed a really important theorem, which is arguably the second most important theorem in the subject after Pappus's theorem. This is the Desargues theorem, which is really beautiful. And it says that if two triangles, say A, B, C, and A prime, B prime, C prime, are perspective from a point, then they are perspective from a line. So I have to tell you what that is, and I'm going to just do it with this diagram. So here in blue is this first triangle, A, B, C. Okay, there it is there. And here's another triangle, A prime, B prime, C prime in green. Okay, and these two triangles are perspective from the point P. What does that mean? It means that if you're at the point P and you're looking towards A, that A and A prime are in the same line of sight. Similarly, B and B prime are in the same line of sight, and C and C prime are in the same line of sight. So if you have that, then Desargues says there's going to be a remarkable collinearity between 3 points which are created by looking at corresponding sides. So let's look at the side AB of the first triangle and the corresponding side A prime, B prime of the second triangle. Okay? These are two lines and they meet in a point. This is this incidence idea, the idea that this point lies on both of these lines. Now, if we look at another, say, line of the triangle, say BC, and the corresponding line of the second triangle, which would be B prime, C prime, then they meet at this point. And there's a third such that can be obtained by taking the third side of the first triangle, which is AC, and seeing where it meets the corresponding side of the second triangle, A prime, C prime, at that point there. So we have these 3 points of intersection, and Desargues says that, like magic, these 3 points lie on a line. Okay, it's a very beautiful and profound theorem, which it's a little bit complicated, but you could get a primary school student, and especially high school students, to draw these things out and to appreciate the magic that's here. Okay, so this is one of those great theorems in mathematics that really ought to be much more widely known. In the 18th century, another French geometer / engineer, his name was Monge, developed another kind of geometry which was ideally suited for architectural and building and industrial applications, and really forms the basis for modern drafting. And this is called descriptive geometry. And it's quite interesting that this geometry is not necessarily widely taught in large areas of the world. So for example, in Australia, I don't know of any actual courses in descriptive geometry. Whereas in Central Europe, like Austria, Hungary, Croatia, Germany, Russia. This topic will be widely studied. So what is the basic idea? The basic idea is that we're interested in a three-dimensional object in space. Let's say, for example, a stapler, okay? So let's say you wanted to describe this stapler in a nice way so that maybe somebody could build it from a design. Monge's idea is that we should have three views of this thing. So we should look at this thing from three different points of view and record each of these views in a kind of a consistent way that allows us to compare them. So let's say the object is this kind of boxy shape that has a kind of a wedge-like thing up at the top. Then if we looked at it from the top down, okay, from the top down, then you might see something like this. Okay, this line here representing sort of that top edge that's coming out there. If you looked at it from the front, well, you'd see this part here, and then you'd see this slanting thing up there, but it would present an image that looks like this. And if you looked at it from the side, well, then you're going to see this sort of cross-section that looks like this. And you can think about that perhaps like this, that you have something like this, okay? Here is one plane, here is another plane, which is perpendicular, and here's another plane, which is perpendicular, okay? So this is maybe like the front and the top and the side. So if we have some object which is here, we can project it horizontally onto the front, or we can project it horizontally to the top, or we can project it horizontally to this side. And after we've done that, then we can open this up and put it on the plane like this. And then there will be various relations between the images of the various points in the object. Okay, so that's the story of descriptive geometry, and it was, I guess, originally Monge's development because he was interested in military applications, building forts and such things for the French. Okay, and this was his new way of designing such constructions so that builders would have an easier time in making stuff. So this is a very interesting and very useful practical side of geometry. Another very major area in geometry is algebraic geometry, which is the study of curves and surfaces, but possibly in higher dimensions and of higher degree. So here is our xy plane of Descartes as before, and now we're looking at equations which are a little bit more complicated. This one's of degree 3 because it has an x cubed and an x squared y term. So x cubed minus x squared y plus y squared minus x equals 1. If you plot the points in the plane which satisfy this equation, or at least approximately satisfy, because actually in practice that's what you do, then you get a shape that looks something like this if you restrict yourself to this portion of the plane. So it's a lot more complicated than the conic sections, the ellipses and hyperbolas and parabolas and such that arise from quadratic equations. So the complexity really goes up as you up the degree of the equations, and algebraic geometry is the study of such things, and it's a fascinating topic. And it's not too much of an extension to say, okay, well, if we look at the analogous things in 3 dimensions, then we should look at equations involving 3 variables, x, y, and z. So, for example, here is a cubic surface. It's still of degree 3, but now it's a surface because it's described in terms of 3 variables, x, y, and z. This in particular is a very special kind of thing. It's called the Clebsch diagonal surface. This is a rather poor illustration of it, but it's some kind of, beautifully shaped thing that kind of goes in and out and such. And this particular cubic surface is quite remarkable because there's all these lines which lie on the cubic surface. In fact, there's 27 lines which lie on it. In the 19th century, institutions of learning in Europe loved to make models of these kinds of surfaces. And still today, if you go to a lot of universities in Europe, you will find some place where they have these models that are sometimes more than 100 years old of these beautiful, sometimes cubic surfaces or quartic surfaces, and they're really lovely things. So this is just the start of what is now a huge topic, but it has its origins in the explicit study of curves and surfaces in 2 and 3 dimensions. It's called algebraic geometry. So I'm only about halfway through my list, so this is going to be the last one for this video. I'm going to have to carry on and tell you about the other geometries in another video. So I want to finish with differential geometry, which is another huge area, which was developed by the German mathematician Carl Friedrich Gauss, who was actually employed as a surveyor in a province in Germany, and so he was actually interested in the practical problem of how do you describe a curved surface, like the surface of the Earth. So roughly speaking, differential geometry concerns itself with parametric surfaces. So these are surfaces in three-dimensional space, but sometimes also curves, but surfaces are perhaps the main interest, which are described in a quite a different way than an algebraic geometer would describe them. Okay? So they're described in terms of parameters. So for example, here is a point in three-dimensional space, u squared minus v, comma, 2uv, comma, v cubed. So there's 3 coordinates here that represents a point in three-dimensional space. Okay, some point in three-dimensional space. But it depends on u and v. So you can think of u and v as being some two-dimensional plane that's sort of off to the side. And for every point in this uv plane, like the point 2, 1, you could substitute 2, 1, and you're going to get a point on this surface. So that's, in some sense, a mapping from this plane to the surface, and gives coordinates to the surface. This kind of surface is, in some sense, more tractable than the algebraic surfaces of algebraic geometry, because we have a concrete way of actually obtaining points which lie exactly on the surface. In algebraic geometry, that's often much more challenging. Okay, so Gauss was interested in this. Euler before him was also interested in this. And one of the standard kind of concerns here is curvature. Okay, so you have a piece of surface. How curved is that? And that depends on a prior notion of curvature of curves. And so it's quite a beautiful theory that turned out to have huge ramifications in the 20th century with Einstein's theory of relativity. Okay, so that's a very brief introduction to a few of the geometries which figured in the European development, but we'll have to say a little bit more about that in our next video. I'm Norman Wildberger. Thanks for listening.